For years, one sentence echoed through the semiconductor industry almost like an unwritten law. Some logic chips simply couldn't be rushed. You could spend billions on factories, import the world's most advanced machines, and recruit brilliant engineers from every continent, yet experience refused to be purchased. According to industry veterans, mastering these processes wasn't measured in months or even product cycles. It was measured in decades. Then something happened that didn't fit the script. China's largest contract chipmaker, SMIC, has now reportedly delivered the third generation of one of its most difficult domestically produced logic chips. Not the first attempt, not a laboratory prototype, the third generation. That matters because every new generation means engineers solved problems that weren't supposed to disappear quickly. Problems involving defect density, process stability, yield improvement, and production consistency. The invisible details that separate a working demonstration from a business. And that's where this story becomes far more interesting than another headline claiming China caught up or, on the other side, that sanctions completely failed. Neither description captures what's actually unfolding. Because the real battle isn't happening inside the chip. It's happening inside thousands of manufacturing decisions repeated every single day. Think about it for a moment. When people discuss semiconductor leadership, they usually focus on nanometers. 5 nanometers, 3 nanometers, 2 nanometers. Those numbers make headlines because they're easy to understand. Smaller sounds better. But ask almost any experienced fabrication engineer, and they'll tell you that the hardest problems rarely appear in marketing brochures. They're buried inside yield reports, contamination control, process integration, and hundreds of tiny adjustments that no press release ever celebrates. That's why TSMC built its reputation over decades instead of overnight. Its greatest advantage wasn't simply owning expensive equipment. It accumulated manufacturing knowledge through millions of wafers, thousands of customer designs, and countless production failures. Every mistake became data. Every failed batch became a lesson. Eventually, those lessons turned into something competitors couldn't simply buy. It's almost unfair, actually. One factory can purchase identical machinery. What it cannot purchase is 20 years of accumulated engineering instincts sitting inside experienced teams. Those instincts only appear after enough things have gone wrong. That explains why so many analysts believed China's progress would eventually hit a wall after export controls tightened in 2022. Without unrestricted access to the latest EUV lithography systems, conventional wisdom suggested SMIC would struggle to move beyond its existing manufacturing capabilities. The assumption wasn't irrational. Advanced lithography dramatically simplifies several production steps, reduces complexity, and improves manufacturing efficiency. But here's the detail that often gets overlooked. Engineers don't stop solving problems simply because the easiest tool disappears. Instead, they usually search for another route. Sometimes that route is slower. Sometimes it's more expensive. Occasionally, it's surprisingly effective. SMIC's reported progress appears to reflect exactly that kind of engineering philosophy. Rather than waiting indefinitely for unrestricted access to technology that may never arrive, Chinese researchers and manufacturing teams have been forced into an uncomfortable position. Optimize every process they still control. Improve alignment accuracy. Reduce defects elsewhere. Extract more performance from older, deep ultraviolet lithography systems. None of these breakthroughs make dramatic headlines individually. Together, though, they begin changing the equation. There's another reason this deserves attention. The semiconductor industry often rewards persistence more than brilliance. An elegant idea is valuable. A production line capable of repeating that idea millions of times with acceptable yields is worth exponentially more. That's the difference between publishing a technical paper and shipping commercial products. We're finally starting to see evidence that this distinction matters. Of course, critics point out, and fairly, that SMIC still trails TSMC at the leading edge. That's true. TSMC remains ahead in advanced nodes, manufacturing scale, customer ecosystem, and access to cutting-edge equipment. None of those advantages disappear because one competitor shipped another generation of logic chips. But maybe that's asking the wrong question. Perhaps the more important question isn't whether China has caught TSMC. Perhaps it's whether the gap is still widening. Because if the distance stops growing, or begins shrinking, then the assumptions driving technology policy over the past several years deserve another look. And interestingly enough, the answer may have less to do with lithography machines than with something far less glamorous: how quickly an entire industrial ecosystem learns from failure. That quiet process, more than any headline, is where the next chapter of this story begins. One of the easiest mistakes to make in the semiconductor industry is assuming that every problem has a technological solution. Sometimes it doesn't. Sometimes it's an organizational problem. Sometimes it's about supply chains. And occasionally, it's simply about how many times a company is willing to fail before finally getting one process step right. That's where SMIC's recent progress deserves a closer look. Building a competitive logic chip isn't like assembling a car where each component arrives ready to install. A modern semiconductor fabrication process can involve well over 1,000 manufacturing steps. Mistolerance by just a few atoms during one critical stage, and an otherwise perfect wafer may never become a usable product. That's why experienced engineers often compare chip manufacturing to conducting an orchestra rather than building a machine. Every instrument has to arrive at precisely the right moment. Now, imagine trying to conduct that orchestra after several musicians have suddenly disappeared. That's essentially what happened after the United States expanded export controls beginning in late 2022. Restrictions weren't aimed only at advanced chips themselves. They extended to manufacturing equipment, electronic design automation software, specialized materials, and even the movement of certain engineering expertise. The objective was straightforward: slow China's ability to manufacture cutting-edge semiconductors by limiting access to the technologies considered most difficult to replace. On paper, the strategy made sense. The logic was that if China couldn't purchase the newest extreme ultraviolet lithography systems from ASML, then advanced manufacturing would eventually stall. After all, EUV dramatically reduces the number of exposure steps needed for extremely dense chip layouts. Without it, producing comparable structures becomes significantly more complicated. Notice I said more complicated. Not impossible. That's an important distinction. SMIC appears to have leaned heavily on multiple patterning techniques using deep ultraviolet lithography, an approach that demands additional processing steps, tighter alignment accuracy, and far greater manufacturing discipline. It's slower. It's more expensive. Yield losses become harder to control. But engineering history is filled with examples where inefficient solutions eventually became surprisingly competitive simply because people kept refining them. The aviation industry did it. The automotive industry did it. Japan's memory chip manufacturers did it during the 1980s. And today, China seems determined to attempt the same pattern inside semiconductors. Of course, this isn't happening because engineers suddenly became smarter after sanctions. If anything, their work became considerably harder. But constraints have a strange habit of forcing priorities. Projects that once depended on imported tools suddenly required domestic alternatives. Universities increased semiconductor research. Local equipment companies received stronger financial backing. Material suppliers accelerated qualification programs that otherwise might have taken years longer. None of this guarantees success. It simply increases the number of people working on the same problem. One often overlooked example is China's growing ecosystem of semiconductor equipment companies. Firms producing etching systems, deposition tools, cleaning equipment, inspection technologies, and specialty chemicals don't receive nearly as much international attention as SMIC or Huawei. Yet together they represent something arguably more valuable than a single breakthrough. They create redundancy. If one supplier falls behind, another continues improving. If one process encounters difficulties, engineers have domestic partners capable of iterating much faster than before. That ecosystem effect is difficult to measure on quarterly earnings reports, but over a decade, it can completely reshape an industry. Here's where I think many discussions become too simplistic. Supporters of China's semiconductor ambitions sometimes argue that sanctions have completely backfired. Critics argue sanctions are working exactly as intended because China still cannot mass produce at the very frontier. Reality sits somewhere between those two positions. Export controls undeniably increased China's costs. Development timelines stretched. Some research programs slowed dramatically. Leading-edge manufacturing remains extraordinarily difficult without unrestricted access to the latest global equipment ecosystem. At the same time, those same restrictions appear to have accelerated China's determination to build domestic capability across areas that previously relied heavily on imports. Both statements can be true simultaneously, and history suggests they often are. There's another lesson buried underneath all this. Industrial leadership isn't only about today's product, it's about tomorrow's engineers. Every production run teaches fabrication teams something new. Every unexpected defect creates another data point. Every design iteration improves future manufacturing. That accumulated experience compounds almost like financial interest. Small improvements repeated thousands of times eventually become major competitive advantages. Remember the idea we discussed earlier, that manufacturing knowledge is really accumulated failure? This is where it begins paying dividends. SMIC's third-generation logic chip may not instantly overturn the global semiconductor hierarchy. It doesn't erase TSMC's enormous technological lead or the sophisticated ecosystem Taiwan has spent decades building. But it may signal something quieter. China isn't merely trying to import semiconductor capability anymore. It's trying to manufacture experience itself. And if that's the real objective, then the next few years won't be decided by a single machine or a single sanctions package. They'll be decided by which industrial system learns faster, adapts faster, and turns setbacks into production knowledge before its competitor does. There's a question that keeps coming back whenever this topic comes up. If China is making visible progress despite restrictions, does that mean the restrictions failed? I don't think that's the right way to judge them. Policies like export controls aren't designed to freeze technology forever. They're designed to buy time. The assumption is that if your competitor needs 10 years to master a manufacturing process, and you slow them down by another 5, you've protected your technological lead for a meaningful period. The problem is that manufacturing isn't static. While one country is trying to preserve its advantage, another is learning how to operate under pressure. Those learning curves don't move in straight lines. They flatten, they accelerate. Occasionally, they surprise everyone. This is where the semiconductor story becomes less about machines and more about institutions. Take TSMC as an example. Its strength isn't simply that it can manufacture at the world's most advanced process nodes. It has built an ecosystem where customers, equipment suppliers, material companies, software developers, universities, and thousands of engineers continuously improve each other. When companies like Apple, NVIDIA, AMD, Qualcomm, or MediaTek develop new products, they aren't just buying wafers. They're contributing experience that eventually improves the manufacturing platform itself. That's an incredibly difficult advantage to replicate. Even if another company purchases similar equipment, it still lacks years of shared knowledge created through countless production cycles. This is why many analysts remain cautious about declaring that China has caught up. They're not ignoring SMIC's engineering progress. They're recognizing that semiconductor leadership isn't measured by one successful chip. It's measured by consistency. Can you manufacture millions of identical chips? Can you deliver them on schedule? Can customers trust your yields? Can you transition smoothly to the next process generation? Those questions matter far more than a single technical demonstration. At the same time, dismissing China's progress would be equally short-sighted. Consider Huawei's return to producing advanced smartphone processors, despite widespread expectations that such products would become impossible. Whether those chips match the efficiency of competitors isn't really the central issue. Their existence alone demonstrated that domestic manufacturing capability had advanced further than many outside observers anticipated. Sometimes a product changes perceptions even before it changes markets. And perception matters. Investors notice. Governments notice. Competitors certainly notice. There's another layer that receives far less attention. Talent. Over the past decade, China has dramatically expanded semiconductor education, increased funding for engineering programs, and encouraged experienced researchers to work across domestic firms. Universities are graduating larger numbers of specialists in microelectronics, materials science, photonics, and semiconductor manufacturing. That doesn't instantly create world-class fabrication plants, but it steadily increases the country's technical capacity. People often ask whether money alone can solve semiconductor problems. The answer is no. But sustained investment in people often can. That's a slower process. It's also much harder to reverse. Ironically, the semiconductor industry rewards patience at a time when politics often demands immediate results. Election cycles last a few years. Factory ecosystems develop over decades. Those timelines rarely align, which explains why public debates sometimes focus on quarterly headlines, while engineers quietly think in 10-year roadmaps. Remember the idea from the beginning that some manufacturing knowledge supposedly takes a decade to master? That estimate wasn't necessarily wrong. The misunderstanding was assuming those 10 years had not already started. By the time the world noticed China's progress through products like the Mate 60 smartphone and newer generations of domestically manufactured logic chips, thousands of engineers had already spent years solving problems behind closed factory doors. Their work wasn't visible because manufacturing excellence rarely is. Success appears suddenly to the public, but internally, it's usually the final step in a very long sequence of small improvements. Here's the reversal I think many people miss. The most valuable product SMIC may be producing today isn't actually a logic chip. It's confidence. Confidence inside China's semiconductor industry that difficult manufacturing barriers can eventually be overcome, even if the path is slower, more expensive, and filled with setbacks. Confidence encourages more investment, attracts more engineers, and convinces suppliers that long-term development is worthwhile. That creates momentum. Momentum doesn't guarantee victory, but it changes behavior. And behavior, repeated consistently across an entire industrial ecosystem, eventually changes outcomes. Which brings us back to the original claim that mastering these chips takes 10 years. Perhaps it does. The more interesting question is whether China's semiconductor industry has already completed the hardest half of that journey without most of the world fully realizing it. The semiconductor industry has a habit of making people think in absolutes. Either one country is winning or another is losing. Either sanctions worked or they failed. Either China has caught up or it's hopelessly behind. Reality is rarely that simple. If SMIC's third-generation logic chip proves anything, it's that technological competition isn't a straight line. Progress doesn't always come from having the best tools. Sometimes it comes from becoming exceptionally good at using imperfect ones. That doesn't mean China has replaced TSMC. Not even close. TSMC still leads where it matters most: cutting-edge process technology, customer trust, manufacturing scale, global partnerships, and the ability to move from one advanced node to the next with remarkable consistency. Those advantages were built over decades and won't disappear because another company announced a new generation of chips. But leadership and momentum are different things. Leadership describes where you are today. Momentum tells you where you might be tomorrow. And right now, China's semiconductor ecosystem appears to have more momentum than many expected a few years ago. Personally, I think both sides underestimated something. Many Western observers underestimated how quickly necessity can accelerate engineering. History is full of examples where countries under pressure developed capabilities that once seemed out of reach. It wasn't magic. It was persistence, backed by enormous investment and a willingness to accept years of expensive trial and error. At the same time, some people celebrating China's progress underestimate how incredibly difficult the remaining journey still is. Moving from one successful product generation to sustained global leadership requires much more than engineering talent. It demands reliable suppliers, advanced equipment, profitable customers, international confidence, and the ability to manufacture millions of chips with consistently high yields. That's a very high bar. There's also a broader lesson here that affects almost everyone watching this video, even if you've never thought about semiconductors before. Every smartphone, AI model, electric vehicle, medical scanner, cloud server, and modern weapon system depends on increasingly sophisticated chips. Whoever masters semiconductor manufacturing doesn't just build better electronics. They influence supply chains, economic resilience, technological independence, and, ultimately, geopolitical leverage. That's why governments are spending hundreds of billions of dollars on this industry. They're not investing in silicon. They're investing in strategic freedom. So, what happens next? My prediction is that the next 5 years won't produce a single dramatic moment where one side suddenly wins the semiconductor race. Instead, we'll see something much more subtle. China will continue reducing its dependence in selected areas while remaining behind at the absolute leading edge. Meanwhile, companies like TSMC, along with the broader Western semiconductor ecosystem, will keep pushing the frontier forward. In other words, both things can happen at the same time. China can improve rapidly, and TSMC can remain the global leader. Those ideas aren't contradictory. They're simply operating on different timelines. Remember the sentence that shaped this entire discussion. Some logic chips supposedly take 10 years to master. Maybe that estimate was accurate all along. The only surprise is realizing that while much of the world was debating whether China could begin that journey, its engineers were already several years into it. And if there's one lesson the semiconductor industry teaches better than almost any other, it's this. Never confuse silence with inactivity. The most important breakthroughs usually happen long before the headlines arrive. If you enjoyed this deep dive, consider subscribing, because we'll keep following the technologies quietly reshaping the balance of global power, one chip at a time.